SwayamPrabha. Digital India. Educated India.
Good morning everybody. We will study today the response of non-premix flame to flow perturbations. So we have done some study of how we can calculate the response of premix flames to flow perturbation. And do you remember how we did this? G equation. So what does G equation do? Tracks the flame front, and then we solve for the flame front. G equation, what is G actually? It is some kind of variable, but it really has meaning only at the flame surface. And now we want to see whether a similar approach can be done for diffusion flames. So we will specifically follow the approach of Balasubramanian and Sujit, and these references are given here. So first one is nonlinear response of diffusion flames to uniform velocity disturbances, combustion science and technology, 2008, volume 180, page 418 to 436. Then the second one is a paper from Journal of Fluid Mechanics on diffusion flames. There are two more from our colleagues, Chakravarti's group, and that's also about non-premix flame. Now compared to premix flame, which has a very large body of literature associated with its response, these are the only papers that you will find about diffusion flames, although nowadays with the reduction of NOx in aero engines, which still uses the non-premix flames, instability in diffusion flames is becoming a subject of interest again. There is a textbook that is available by T.C. Lewin called Unsteady Combustor Physics, Cambridge University Press. Chapter 11 of this book has a consolidated treatment based on those papers which I mentioned. Now, so this is a very recent textbook. So you must have all heard about classical diffusion flames. This is the pioneering work by Burke and Schumann, which is why these flames are called Burke-Schumann flames. This is in 1928. So we will follow their approach, and now we are specifically interested in looking at the unsteady problem. Burke-Schumann studied the steady problem. Now we are having flow, and it has the flame can get oscillate and wrinkle and so on. So those are the phenomena which are very similar to those you would see in premix flames, but there are some differences. So let us take a look at the geometry. So this would be a over ventilated flame, and you will have, this is the center line, fuel, So this would be the classical Burke-Schumann configuration or geometry. So you have fuel coming through a slot, and we are considering 2 dimensional here. You can work out that for axisymmetric also, 2 dimension is simpler, and you have fuel coming inside, oxidizer coming outside. You can work out for the opposite also, but this is the classical configuration, and there will be a flame here, which is the diffusion flame, and this is usually of course you can also have other flame configuration where the flame is coming and attaching on the walls and so on. So this is over ventilated. We can have under ventilated flames also, then it will go on that way. So how do you analyze this problem typically? So we do this in the framework of, what is the formulation we use? Anybody studying combustion here? Schwab-Seldovich formulation. So what do you get in the end out of Schwab-Seldovich formulation? Do we know this, or should I do it? I think I will do it. So let us say we have of course we can actually solve both in the case of premix flame and in diffusion flame. We can solve the conservation of species equation, mass, momentum, energy, everything, and we can solve the full flow field, and we can get the reaction rate out of it. But why did we use the G equation approach? Because it was very simple. Okay, so the same way we will try to get a simple partial differential equation which we can solve to get the problem. You can of course do more complicated analysis, but this is the simplest possible way to do it, and where some analytical solutions are possible. So let us say we have some kind of reaction, product. So we will write the species equation for x and y. Star would mean dimensional, and without star will be non-dimensional. D is diffusivity. Omega is the reaction rate, and Wx is the molecular weight of x. Omega can be written as B alpha x alpha y e power RT. So similarly, so similarly, if there is any mistake, please point out. So similarly, we can write the equation for y also. So we can see hints of advection diffusion equation here, which is a very famous equation and solved, but we have some unnecessary or some other term which we cannot handle. So now we have to get rid of it. How do we do this? The way to do it is we should divide this alpha x wx down, here also alpha y wy, and then you will have omega, and if you subtract then omega will go away. So that is the key. So if we can define our new variables, scale variables, and we define z as x minus y, that there is a difference between the scale mass fractions. So z is called the Schwab-Zeldovich variable. So if you redo this, you get so I subtract this from this, so I will get x minus y is z, and we write the equation in terms of this. Sorry? Plus, yeah, thank you. So if I have this, are there any questions about? Yeah. Thank you. Thanks. So I made a mistake here. Alpha y. So this is the advection diffusion equation. So if you compare this equation to the G equation, there we had so the left hand side of the equations are quite similar, but here the right hand we have SL times del G over there, but here we actually have a diffusion operator here. So that's the that's the difference. So there is some similarity, but there is some difference. The other similarity is that okay, we are writing it in terms of one variable, but the difference is that Z is a physically meaningful variable everywhere in the field, and you have to solve for it all together, whereas G we can G is just defined as G is has one sign on one side of the flame, another sign on the other side of the flame, and at G equal to 0 there is a flame. So we can actually say like y minus psi is G, and so at G equal to 0 y equal to psi, and write equations directly for the flame surface in premixed flame, right. That is what we did. So we said that and then we put this equal to 0 and then directly write a equation for the displacement variable. So we can't do that here because Z the Schwarzschild of which variable that it's a physical variable everywhere and we have to solve for it everywhere, and then we can actually find the flame surface by how do we find the flame surface. So the assumption is that the flame stands at the stoichiometric surface. So we have to find what is the Z stoichiometry, Z corresponding to stoichiometry, which is this scaled x star, so this x minus y corresponding to the stoichiometry, and that would be the flame surface. So from that we can get the flame surface and then we can track the flame movement. I hope this is clear. So there is some strong parallel, but there is some strong differences also between diffusion flames and premix flames. Even in the results in terms of the transfer function we will see some strong parallels and some differences. Now we will proceed to solve for it. So we need to apply boundary conditions without which we cannot solve any problem. So let us examine what are the boundary conditions here. So here in the inlet there is fuel, there is oxidizer. In reality you can have the oxidizer can diffuse and the products can actually diffuse into the fuel stream. Similarly fuel can diffuse into oxidizer. So we will ignore those effects and we say that here at the inlet plane in this location we have fuel, so we will have no oxidizer, and in this location we have only oxidizer at the inlet plane. So that is the way we are going to enforce the boundary conditions. Just need one more notation. I am following the symbols from the textbook on by Tim Leuven on combustion dynamics. So this half width is W1, this half width of the outer tube is W2. Okay. So this basically means that in the oxidizer tube we have oxidizer and in the fuel tube we have fuel, that is all. And enforcing this boundary condition also enables us to obtain a analytical solution, as opposed to if you enforce the flux boundary condition you would have difficulty in getting analytical solution. So in reality there is axial diffusion of fuel into the oxidizer and vice versa, that axial diffusion of oxidizer into the fuel. So the solution must be obtained over a larger domain that includes the supply lines of fuel oxidizer. So I think let us correct the figure, let us call this bigger outer tube at W1 and this is W2. So this boundary condition implicitly neglects the axial diffusion at x equal to 0, and we can assume symmetry boundary condition at the center line, right. So and no diffusion should happen through the walls because you have rigid wall. and as x tends to infinity, Z must attain a finite value finally. So, we will derive a solution in the limit of small perturbations, that is we expand everything as some 0th order plus first order or a base flow plus perturbation, and then we can get the solution. In fact, you do not need to do this because our equation is a linear equation provided u is a input and you can see it is a linear equation. So, we do not need to do it, but it is very convenient and will enable us to work out analytical solution. So, we will do that. So, any parameter, I am following Lou-Evans notation, which is a function of x and t, can be written as some base flow So, with this approach we will be able to derive an explicit analytical expression for the flame surface, and this will be very nice in looking at the controlling features of the flame dynamics. Okay. So, first we will study the problem in the absence of forcing, so that we can get the steady solution, and then we will look at the problem with forcing. So, in our previous notation this would be Z bar and U bar, but I am just following Lou-Evans book here, so that you can follow it also. So, this can be solved with separation of variables. I can work it out next class, but I just want to write the solution here. So, just try if you would get this. Actually, you should get some more complicated expression here, but then if you take Peclet number tending very large, then it should reduce to this expression. So, I will just let you work this out, bring it next class, and then we will see what you got and what I have. Now, this quantity Peclet number, maybe in this class we are introducing for the first time, so it needs some explanation. So, Peclet number physically corresponds to the, of course all numbers correspond to ratio of time scales or length scales or something like that. So, here it corresponds to the relative time scale, ratio of the relative time scales for the two phenomena, convection and diffusion. So, we want to transport mass over a distance W2, that is this, and what are the time scales involved. So, so basically we want tau diffusion divided by tau convection. So, tau convection is pretty straightforward, the distance divided by the velocity. Now, what is tau diffusion? So, let us do a little analysis. So, this is the heat equation. So, if you so if you get the length scales, so this is the length squared over diffusion, that is the diffusive time scale. So, this is the formula for equal to Beckley number PE. So, people write Beckley number for convection, Beckley number for diffusion. So, both are referred to by the same Beckley number, but here it is, we are talking about diffusion. So, how do you, so having got a expression for the Z0, the Schwab-Seldovich variable, how do you determine the where the flame sheet is? So, what is the assumption in Burke-Schumann? So, the flame is like a sheet. Means we are the inherent assumption in Burke-Schumann flame is that you are having infinite reaction rate compared to the other processes. Reaction rate is much faster compared to convection and diffusion. So, the flame is really thin sheet, and this happens. So, you solve for the Z field, and where you have the stoichiometric contour, wherever you have, so you have fuel diffusing out, oxidizer diffusing in. So, there is a field of X and a field of Y, right. There is a fuel mass fraction as contours, oxidizer mass fraction contours. So, somewhere, so if you look inside, you will have more fuel compared to oxidizer, because naturally fuel is coming out. If I look somewhere here, there will be more oxidizer than fuel, because fuel is diffusing out, but predominantly it is oxidizer. But somewhere down in between, the concentration would be equal to of both fuel and air will be that of stoichiometric mixture, and the flame stands there. So, this is the flame sheet assumption. So, we use that to locate the position of the flame. So, this is the assumption in a real non-premixed flame. For example, you will have other phenomena such as triple flame, flame standoff, and so on, because the walls may quench. So, reaction may not happen here. So, there may be a little bit premixed mixture here, and so on. So, there are those complicated finite rate chemistry effects that happen, but here we do not have any of that. So, because we are referring to classical Burke-Schumann. So, all we have to do is to take this and put Z0 as ZST, and this would be the flame position, okay, and it will be implicit expression. So, you will have to solve backwards, or iteratively or something. I will work out next class, I told you the full solution, but it's there in this solution. Just try this out. You can take that equation and use separation of variables. If it doesn't work out, I will do it next class. Now one remark I want to make is, suppose you are solving in a circular geometry, then can you imagine how these expressions would look like? They would be in terms of Bessel functions, yeah. So that's the difference. Here it will be in sines and cos because we are in a 2D geometry. So next we want to get the flame length. So we just have to put this term as 1, so that way you will get the maximum position, and that is the flame length. So in the thermoacoustic problem, this duct will be long and there will be acoustic field, and there will be a certain velocity fluctuation here which will affect the mixing here, right, I mean which is governed by the advection diffusion equation. That would result in the flame fluctuating, it will result in the heat release rate fluctuating. Now that will drive the acoustic field, which in turn will give the feedback. So now we are not studying that problem here, I am not working out in the class, but we one of the references in that list talked about that. But here what I am going to do is to impose a velocity fluctuation here and see what happens to the flame. So will the flame dance, will it wrinkle, will it move up and down, that kind of thing. So what we have is a base flow field, that is, even if there was no fluctuation, you will have fuel and oxidizer and they will diffuse out and there will be a flame. Now perturb it with certain velocity fluctuations. How can you do a velocity fluctuations? You say u is mean plus u bar plus some u prime, and u prime goes like some sin omega t, or in an experiment you can put a valve and fluctuate the flow rate or something like that, and then see what happens to the equation. Our advection diffusion equation is an unsteady equation. We drop the steady term to get the base flow, but now you have to put the term back in and solve for it. So what we need to do is to, so ux naught was the base flow in this convention, ux1 is the perturbation, and I just follow the convention in this textbook of Leuven, and we had so if you split it as z naught plus z prime, what you will get is So this will have a mean time fluctuation here plus mean here time fluctuation there. Okay, so that's why the two terms. So this is the perturbed equation. I will, yeah. Epsilon is like a how much, like you have, so the total U equal to ux comma. So this is the total velocity field. So epsilon is like what is the like the amplitude of the perturbations as a fraction of the mean velocity. Clear? So again we can solve this, try to solve this, it will be an interesting exercise. If you don't get it, that's completely fine, I will solve it here in the class, but just try it, it's kind of interesting, I think. No, f is, I mean 2 omega is 2 pi f. We can simplify the expression, because if you take a look at the expression for z naught and if you differentiate it, you will get this scaling term sitting in front. We had the formula for z naught in your book. So if you use this, these terms are, that's here, so you can write without the sigma as z1 equal to see ST W2 is equal to F W2 over Ux comma 0. Now let us multiply top and bottom by LF and LF. So this can be written as F LF Ux comma 0 into W2 by LF. This is equal to ST LF W2 by LF. So this we have used in here, and you get this expression. So please check on this. So this is the expression for the perturbed Z field. So you have the base flow plus the perturbed Z field. Now we have solved for the entire thing, although that is not what we are looking for. We just want the final what happens to a flame, but there is no option but to solve for this. Now from this we want to look at what happens to the flame and how the flame oscillates. We will do that next class, and we will also look at the derivation of these things in case you are having difficulty. So stop here now.